On June 3rd, 1997, 35 meters from the net, a defender placed a leather ball on the grass. 70,000 fans in Lyon watched him take an unusually long 30-step runway back. He began sprinting forward at peak athletic speed. His left foot struck the ball at 84 miles per hour. The ball launched far to the right of the defensive wall. It was heading straight for the ball boy standing 10 feet off target. The ball boy ducked in terror. French goalkeeper Fabien Barthez didn't even move. He assumed the shot was wildly out of bounds. Then, something impossible happened in midair. At 20 meters out, the ball suddenly veered violently to the left. It defied every basic human visual expectation. It clipped the inside of the left post and ricocheted into the net. Barthez stood frozen in disbelief. Physicists around the world dropped their coffee cups. For decades, people called it a miracle or a physical glitch. But nature does not make mistakes. What actually happened in those 0.2 seconds of flight? To understand this optical illusion, we must look at invisible ocean currents above our heads. We live at the bottom of a heavy, dense sea of nitrogen and oxygen molecules. Air is not empty space. Air is a viscous fluid that exerts 15 pounds of pressure on every square inch. When a smooth sphere travels through air, molecules collide with its front surface. At low speeds, air flows symmetrically around both sides of the ball. The pressure on the left equals the pressure on the right. The ball moves in a predictable straight line. Gravity eventually pulls it down in a standard parabolic arc, but what happens when you make that sphere spin rapidly while moving through space? In 1852, a German physicist named Heinrich Gustav Magnus was studying lethal artillery shells in Berlin. German military officers noticed cannonballs were straying strangely off course on windless days. Magnus set up brass cylinders in his laboratory to track airflow dynamics. He discovered an invisible force field created by rotation. When a ball spins counter-clockwise, the left side of the sphere moves forward against oncoming air. This creates high friction and high air pressure on the left side. Simultaneously, the right side of the ball moves in the exact same direction as the airflow. This creates low friction and low air pressure on the right side. High pressure always pushes toward low pressure. This pressure imbalance creates a sideways push called the Magnus force. Is a simple pressure difference enough to bend a heavy leather ball mid-flight? The math says yes, but the story gets much stranger. When Roberto Carlos struck that ball in 1997, he didn't just spin it. He imparted 10 full revolutions per second onto the sphere. That means the leather surface was spinning at over 800 revolutions per minute. A thin layer of air molecules clung directly to the leather stitches. Physicists call this microlayer the boundary layer. As the ball flew through the stadium, it was dragging a miniature tornado of air along with it. This boundary layer delayed airflow separation on one side of the sphere. Air was deflected sharply off the back right side of the ball. According to Isaac Newton's third law of motion, every action triggers an equal and opposite reaction. Because air was pushed backward to the right, the ball was kicked violently to the left. But that still doesn't explain the most terrifying detail of the goal. If you watch the footage closely, the ball didn't curve smoothly in a gentle circle. It traveled completely straight for 20 meters, then snapped violently sideways at the last second. Why did the trajectory suddenly break halfway through its flight? In 2010, a team of French physicists led by Christophe Clanet and David Quéré set out to solve this exact mystery. They built a high-speed underwater catapult at the École Polytechnique in Paris. They fired plastic spheres at varying velocities through high-density liquids. They tracked the precise pathways using high-speed digital cameras recording thousands of frames per second. What they uncovered shocked sports scientists worldwide. The true trajectory of a spinning sphere is not a curve. The true trajectory is a spiral shape called a teardrop curve. At initial launch speed, air resistance creates extreme turbulent drag around the leather seams. At 84 miles per hour, the ball moves too fast for sideways lift to dominate. Forward momentum overpoweringly masks the sideways Magnus force during the first half of flight. To the human eye, the ball appears to be traveling in a straight line, but as air resistance gradually slows the ball down, forward velocity drops significantly. When the ball drops below a critical speed threshold, forward inertia loses its dominance. The rotation speed, however, barely decays at all. The sideways Magnus force suddenly takes complete control of the object's flight path. The arc abruptly bends into an aggressive, sharp hook. It looks like an invisible hand reached down from the sky and slapped the ball sideways. Have you ever wondered why your own brain fails to predict this sudden shift? Human visual systems evolved over 3 million years on African savannas. Early human hunters needed to calculate the flight paths of rocks, spears, and jumping prey. None of those natural objects spin fast enough in midair to generate fluid dynamic lift. Our visual cortex developed built-in neural prediction algorithms optimized strictly for simple gravity parabolic arcs. When a ball follows a Magnus spiral, the motion violates your brain's internal physics simulator. Your eyes see a straight trajectory and project a safe trajectory far outside the goalposts. Goalkeeper Fabien Barthez was not lazy or careless. His human visual cortex recalculated the ball's trajectory based on standard evolutionary physics. His brain concluded with 100% certainty that the ball was missing by yards. By the time the ball entered the Magnus breakdown zone, human neural processing limits were overwhelmed. A human nerve impulse takes 0.1 seconds to travel from retina to motor cortex. Muscle activation requires another 0.1 seconds. Barthez was physically trapped inside his own biological processing delay. He remained completely still because his brain literally had no time to rewrite reality. Can this legendary trajectory ever be replicated on demand? Christophe Clanet's team calculated the exact mathematical equation required to produce the perfect Magnus spiral. You need a strike velocity exceeding 30 meters per second. You need a surface spin rate exceeding 60 radians per second. You need an impact point exactly 1.5 centimeters off the center axis of the ball. You need to minimize ball deformation at the moment of foot impact, and you need a precise distance of 35 meters to allow the velocity decay curve to trigger. If the wall is closer than 20 meters, the hook happens behind the goal line. If the strike speed drops by just 5%, the ball hooks too early into the wall. Roberto Carlos did not solve advanced fluid dynamic differential equations in his head before running up. His body relied on thousands of hours of instinctual neuromuscular trial and error. Through relentless practice, his muscle memory stumbled upon a narrow mathematical sweet spot in atmospheric physics. But modern technology is quietly changing this ancient battle between physics and human instinct. Modern match balls are no longer stitched together with 32 traditional leather panels. Synthetic thermal bonding creates smooth, seamless surfaces with shallow aerodynamic grooves. At high speeds, these smooth synthetic surfaces enter what aerodynamic engineers call a drag crisis. Chaotic air currents form unpredictably around smooth panels. This creates the erratic, dancing movement known as the knuckleball effect. Instead of a predictable, violent Magnus spiral, modern balls wobble randomly in multiple directions. Airflow switches from laminar to turbulent without warning halfway through flight. Goalkeepers now face unpredictable physical chaotic systems on a weekly basis. Is human physical skill being replaced by deliberate aerodynamic engineering? FIFA carefully regulates ball weight, circumference, and internal pressure before every major tournament. Yet even tiny changes in surface texture drastically alter how air molecules stick to the boundary layer. The 2010 Adidas Jabulani ball became notorious for defying standard goalkeeper predictions in South Africa. Aerodynamic testing at NASA Ames Research Center revealed the ball had unique high-speed turbulence thresholds. Strike a sphere slightly too soft, and it behaves normally. Strike it slightly harder, and air boundary layers collapse midair. Players spent months adjusting their foot striking angles to account for fluid dynamic chaos. But no modern synthetic ball has ever replicated the eerie perfection of the 1997 shot in Lyon. That single strike remains the gold standard of applied atmospheric physics in human sports history. It proved that human limbs can tap directly into complex fluid mechanics without understanding a single line of calculus. Every time a ball is kicked on Earth, it interacts with air molecules forced aside by its trajectory. Millions of invisible collision events take place during every millisecond of flight. Air molecules compress, expand, rotate, and exert microforces across the leather skin. We spend our entire lives swimming through an ocean of invisible air we rarely notice or think about. It takes a moment of athletic brilliance to make that invisible sea visible to millions of viewers. When you watch a football curve across a stadium grass field, you are watching invisible fluid pressure gradients at work. You are witnessing Isaac Newton's laws interacting with Bernoulli's pressure principles in real time. You are seeing 3 million years of human evolutionary optical limitations exposed on live television. What felt like magic or a miracle was simply atmospheric physics operating without compromise. How many other invisible physical forces are constantly shaping the outcomes of our daily lives without our awareness? Gravity pulls down on us constantly. Friction keeps our feet grounded on paved walkways. Air resistance slows down every gesture, every step, and every throw we attempt. We live inside a massive physical framework ruled by strict mathematical equilibrium. Athletes push human physical bodies to the absolute boundary of what those physical laws permit. They master precise angles, forces, and rotational speeds through pure physical repetition. They turn fluid dynamics into fine art on open green fields. And for one brief second in 1997, a defender made air itself bend to his absolute will. The ball boy ducked because he trusted his ancient evolutionary eyes. The goalkeeper stood still because his biological visual processor timed out. The ball curved inward because fluid dynamics obeys mathematical certainty rather than human expectation. We spend our lives believing our eyes show us objective reality, but our vision is merely a simplified survival model built for primitive environments. When nature introduces rapid rotation and fluid pressure, our mental reality breaks down completely. The universe is not bound by what feels intuitive or logical to human observers. It is governed by silent, unyielding physical equations operating everywhere all the time. Roberto Carlos didn't break the laws of physics on that warm summer night in France. He simply reminded 70,000 stunned witnesses that air is real, dense, and immensely powerful. The game of football isn't played between two teams on a pitch. It is played between human intention and the invisible physics of the world around us.